So as we were saying, there's just no way to come up with this prime factorization of large numbers. Okay, and that's good, because if we want to do cryptography, that's why we go this route. We don't want it to be easy for somebody to crack. Okay, now there is an efficient way to compute the GCD of two numbers without actually going and finding prime factorizations. Give me two numbers and I can write an algorithm that will find the greatest common divisor, or we might consider greatest common factor of the two numbers. We can do that, and that ends up being good enough for what we want to do later. Okay, so that's what we're going to learn today, is how to come up with the GCD of two numbers. That's all we want to do. We want some efficient way to do that. And we're going to find we can do it. Okay, so here's the theorem that we need in order to do this. It's called the GCD theorem. And it says, let's start with two positive integers. We're going to call them X and Y. Let's start with those. And then what they're going to tell us is that the GCD of those two numbers, X and Y, is the same GCD as we would get if we were finding the GCD of two other numbers. Okay, what are these two other numbers? One of them is one of the original. See, the X was in both. But the other one is not the other original, but it's that other original mod the other original. So it's Y mod X. That is another number we can substitute in instead of Y. And we can find the GCD of these two new numbers, and it'll end up being the same GCD. Now let's see why that will be helpful. Let's look at this example that GCD, let's say we're trying to find the GCD of 51 and 24. Well, this theorem tells us that the GCD of 51 and 24 is also the GCD of 24 and then 51 mod 24. Okay, so you take the largest number and then mod the smaller number. And that's our other number that we're going to compare to the 24 and find the GCD of those. Now, is that going to help us? Well, 51 mod 24 ends up equaling 3. And 24 and 3, it's going to be a lot easier to find the GCD of 24 and 3 as it is to find the GCD of 51 and 24. And as you can imagine, if you have larger numbers, then it could only get, help. It can only help to apply this theorem, okay? To start with larger numbers and then get down to a set of smaller numbers, okay? So that's the idea. But here's what we're going to do with the Euclid's algorithm. We're going to use that, and we're going to keep replacing the largest number with a smaller number until we get down to really small numbers that we can really work with, okay? So here's what Euclid's algorithm says. I'm going to go over this, but then we're going to see it done. So hopefully you'll see that it's pretty understandable, hopefully, what we're doing. So assume that we start with two large numbers, and we're going to assume that Y is bigger than X. And if not, then we'll call YX and XY. Okay, so basically we're going to call the largest one Y and the smallest one X. Okay, now according to the GDC theorem, Y can be replaced with this value here in the computation in order to find the GCD, right? That's what we just saw. And so we can do that. And so we can use this X mod X along with X to find the GCD and find that it's the same GCD as for the original two numbers. Okay, and as we saw in that example, since it's going to be a smaller number, Y mod X is going to be smaller than both X and Y, then we'll compute the GCD of Y mod X along with X instead of, with this one, instead of the Y, it's going to end up being an easier problem. Okay, so, but what we're going to do is continually, repeatedly take the mod function until our numbers get down so low that they're so small we can work with them without even a calculator. But we'll have to use a calculator or a computer or something when we're first doing these mods because they're going to be big numbers, right? But anyway, but we're going to keep doing it at least until it's easy to find that GCD. Okay, so we'll see how it's done here in a second. But the bottom line is we keep going until we find our two X and Y's. We keep reassigning what X and Y are. X and Y start as the original numbers, and then they keep getting smaller and smaller and smaller until eventually we're going to find that this is true. Y mod X, now with our new X and Y, ends up equaling 0. Now you might think, well, that can't happen all the time, no matter, it would depend on the value, what our original numbers were that we started with. But it turns out that it does happen all the time. We will eventually, if we apply this theorem and keep taking this mod and replacing the numbers, we end up getting down to our last two numbers giving us this relationship here. And at that point, when we have those last two numbers giving us this relationship, then the number on that step that's considered X is going to be the GCD of that original set of numbers that was very large, okay? So we've just talked through this, but you haven't seen it done. So don't worry if it still seems a little foggy, okay? But we're gonna do it and you'll see that it's really pretty easy, okay? So let's start with this. We're going to use Euclid's algorithm, and that's what that is that we just talked about, to find the GCD of 153 and 117. Okay, so we start with putting those two numbers down here over to the left of our paper or the screen or wherever you're working. Okay, and you want to start putting the largest number first. Okay, that's because we're going to get smaller and smaller numbers as we move to the right. Okay, so largest number here and then the next here. We want to find the GCD of these two numbers. Okay, the first thing we're going to do is remember that, that theorem said that we can take the largest mod the smallest and get another number and use it, right? So we're going to take 153 mod 117 and see what number we get. Now, I'm not going to have us take the time to do it. You'd have to use your calculator or somehow be able to come up with this. And these aren't, when it's bigger numbers, it's not real obvious right away, especially if we don't want to use our brain power for that, because we have a lot of stuff to do to use our brain power for. So I'm going to, in all of this, just tell you what these values are when we use the mod function, and you'll just know that you could go find that yourself. Okay, but anyway, it turns out we get 36. Okay, so now what do we know now? Because of that theorem, we know that we can now start looking for the GCD of these two numbers here and forget about that big one, right? Because that's what it said. Just take this other number and then look at those two and find the GCD. Turns out you'll have the same GCD as if you were looking at the original. Notice what we had to do to get that 36 was look at the two previous numbers, right? 153 and 117. At that point, that's all we had. But as we go further and do more and more steps, we're always going to look at the two previous numbers, okay? So let's go on. We're going to replace 36. We're going to go on down here, and we're going to use the previous two numbers, 117 and 36. So we're going to look at 117 mod 36 and find out what that number is. That turns out to be 9. Again, how'd we do that? We used the two previous numbers. At this point, we've forgotten about 153. We don't care about that anymore because we want to keep getting smaller, okay? So now we're down to 9, but we want to keep going. So the next one would be, we're going to find another number to put here, and we're going to use these two previous numbers, 36 and 9, okay? So we take 36 mod 9, and that ends up becoming 0 because 9 divides 36. And again, we used the two previous numbers to find that. So we just went through what that previous slide said to do for Euclid's algorithm, but then the bottom line of Euclid's algorithm said that once we get down to 0 here, it ultimately turns out that it's the one right before it. If you eventually get down to 0, the number that we're going to get right before we got 0 ends up being the GCD. Okay, so we see 0 here, so we step back 1. This is the GCD. So now we can say that 9 is the GCD of not only some of these other combinations, but also of this original set of larger numbers. So 9 is the GCD of those. Okay, so again, we start with the 2, keep doing the mods here, using the 2 previous numbers, and then get down to 0, and then step back 1 step, and whatever a number is right here before the 0, that's our GCD. Okay, does anybody have any questions on that? Okay, so we could say that 9 is the GCD of those. Okay, let's do another example. We're going to use Euclid's algorithm to find the GCD of 675 and 210. Okay, so again, we write the 2 numbers and write the largest one first. Okay, and we will have a time today where I work with, you know, I write with a pen and paper, or you'll see it on the screen. And so you'll be able to write along with me at that point. But here early on, I just wanted you to see this done fast so that you start to see the pattern. But you will get a chance to kind of do some of this on your own with paper and pencil here before we're done. Okay. Okay, so 675, 210. So what do we do first? We're going to look here and say we want to find 675 mod 210. And we find out that that is 45. Now we go on to the next blank area, and we're going to use the 2 previous numbers, which is 210 and 45, and say 210 mod 45, and we get 30. And then we do it again. So now we're going to use these 2 numbers here, 45 and 30. So 45 mod 30, and we get 15. And we haven't gotten to 0 yet, so we keep going. So one more, we're going to take 30 mod 15, and we finally get our 0. Okay, so we've got our 0, and now we know that once we get to 0, we know we can find the GCD by backing up 1 step and seeing what the number was before we got 0, and it's 15. So we would say that the GCD of those 2 originals, it's also the GCD of some of these others, you know, any pair of any of these, but we really didn't care about any of these, you know, ultimately we just wanted to know this, but we used all of these smaller numbers to get this. But anyway, so now we can say 15 is the GCD of those 2 original numbers. Okay, is that making sense? Any questions on that? Okay, let's go on. Now, they provide for us an algorithm that would do what we just did. They show that this is what we could use, and we're using pseudocode again here. So I want to show you, and so you can look at this algorithm and see how it is similar to what we just did. So remember, for the first one, we started out with 153, 117, and then we went down to 0. Okay, so let's see how this relates to what we just did over here. So it says we're starting with 2 numbers, X and Y, and we want to output the GCD of it. Okay, so it says if Y is less than X, then swap, because again, we want the Y to be considered the largest. Okay, so here, pretend like 36, 9, and 0 aren't there. All we would have is 153 and 117, and we're going to call the largest one Y, and then we're going to call the other one X. Okay, so we've gotten that far. And then we define a new variable called R, and it's Y mod X, right? So 36 we got from taking 153 mod 117. Okay, and we got R, so we would call that R. Okay, now here's where we start progressing, because we've got a loop. It says, as long as R is not equal to 0, then switch up these variables. And in the old X should now be a Y. the old R should now be X, and we should have a new R over here. So watch what happens. I'm going to click on this and those move over. Now we have a new Y, and that's what happened when we did what's inside the loop here. This all moved over. So now Y is 117, X is 36, and then R is 9, okay? And so we did that, but now we keep doing it. We keep moving down until R becomes 0. So we're going to move down again. We move those down again. And we finally, when we get to this point, we have a brand new X and Y, right? And we finally got our R of 0. So we can stop right there and then see what happens after the loop. After the loop, it says return X. So there's where we go. We said we go to the number right before our 0 for R, and that would be the value we would return. So in this case here, it would return a 9. Okay. Now you won't have to write this algorithm out or anything. I just wanted you to see that, how what we're doing relates to what they came up with for this algorithm. But what you do need to do is be able to do perform this by using actual numbers, like we did in the last screen, and like we'll do, and we're going to be doing some new things here soon too. So I'll show you when I start writing things out. That's the kind of thing you'll know that you have to be able to do. Okay. Okay. So now this is just kind of a reminder screen, just so that you'll understand one thing that's said on the next screen. Okay. I could just have said, we learned this already, and I should have probably done that. So not to confuse you, but I just wanted to just remind you here. Last time we talked about the division algorithm, which said that if we have two numbers, n and d, we can write them this way: n equals some number times d plus r. And we said that if we write it that way, it turns out that what goes in front of d is the value n div d, and what goes in place of r is n mod d. Now that might not be making much sense right now, but let's just look at this example. I have two numbers, 13 and 4. All this is saying is I can rewrite 13 as something times 4 plus something else. And the thing that goes in front of the 4 is what's for that q, which is n div d, which is 13 div 4. And then plus, and then what goes here is 13 mod 4. So if I have two numbers, I can always write the largest number as this, the largest div the smallest plus the largest mod the smallest. Okay, so just keep that in mind as I go to the next screen. Okay, so but again, this is just kind of a remember that, and we'll need to use it here next. Okay, so now let's go and continue on. It turns out that for what we need to do, which is ultimately to find the multiplicative inverse, mod some number, we need to do more than just find the GCD. We've learned how to find the GCD of two numbers with using Euclid's algorithm. And we're still going to be needing to start at that point, but it's not quite good enough. We also need to be able to write that GCD as a linear combination of those original numbers. Okay, so if I start out with two large numbers, x and y, I need to not only be able to find that GCD, but be able to find some numbers s and t, so that I can write that GCD as some number times one of my original numbers, plus then some other number times the other original number. So this is going to be where we're really needing to look and find. So that's where the rest of the algorithm comes in. We need to learn how to do this. Okay, that's what we're going to learn now. Okay, so here's where I said we know that y can always be written as y equals dx plus r. That's what I just showed you. Take a number, and I can always have the other number times the one number, div the other, and then plus R, which is the one number mod the other. Okay, so if you didn't remember that, you know, and if you're still confused about that later, you can go back and look at that previous slide. But it turns out that's true. Okay, we can always write one, if we have two numbers, we can write one in terms of the other using this pattern. But if I took this equation here and solved for R, this is what I would get. Okay, R equals Y minus, and then Y div X times X. This pattern is very important, and you need to start recognizing it. Right now, it looks a little weird, but you're going to use this pattern and pull it out of the top of your head over and over, hopefully. Okay, so let's just look at that again. Well, I'll look at it and we'll look at it in the examples, and then you'll see it over and over. But let me just say this. Notice the Y, which remember Y is going to be the larger number. We started with that, saying the Y would be the larger number. So when we write R as something that has to do with our two other numbers, see the Y is mentioned first, and then the smaller number is mentioned next. But we have this minus and then this here. So this is what we need to learn so we can use it. But anyway, so what we're going to have happen is each time we iterate through that loop in Euclid's algorithm, you know, we find a new R, then we're also, besides finding that new number that we're going to then continue all the way down to 0, we also have an equation that we can come up with based on this pattern. Okay. Given an X, given a Y, X, R, no matter where we are on that sliding long line of numbers, we could always write R as Y minus, and then in parentheses, Y div X, then times X. So again, the largest number goes here, the other number goes here. So we can always come up with an equation like that for each time we get a new R. And that's going to be important. We're going to need to do that. Besides finding all of those R's and getting down to 0 so that we can find our GCD, we're going to collect all those little equations that we get. And then we can use those by a series of substitutions in order to come up with this very important situation here, where we're able to write the GCD of the original numbers as a linear combination of those original numbers. So we'll see an example here, but that's our goal. Okay, so we'll use all of that to find those coefficients S and T so that we can use the GCD, have an equation that says a GCD equals some integer times X plus some integer times Y. Now, those integers might be negative. They usually end up having some negatives in there. Okay, but doing all of this by using these equations and doing this series of substitutions, along with finding all those R's, that's called the extended Euclidean algorithm. And so that's what I want you to know how to do before we're done here today. So that's why I wanted to spend the whole time on it. So you already know how to do that first part, getting all the R's down to R equals 0. Now we need to learn this next part here, okay? And remember this little pattern here, okay? Any questions so far? I know at this point it's maybe a little foggy, but you'll see some examples here. But any questions? Okay, if not, I'll go on. So we're going to use that whole thought that we just talked about, and it's going to be called the extended Euclidean algorithm. I guess I'm going to get to an example here. But, you know, like I said, I think I pretty much already said this in the last slide, but we're going to use that Euclid's algorithm. I think they call it Euclidean algorithm sometimes too, but we're going to do that first, but then we're also going to collect the set of equations. And then we're going to use that set of equations to eventually be able to write the GCD as a linear combination of those two original numbers. And again, it's important that we know how to do this. I can just tell you just to take my word for it. Otherwise, I wouldn't be spending all this time on it. Okay. Okay. So let's go through this. Write the GCD of 153 and 117 as a linear combination of 153 and 117. Okay. So first of all, we don't even know what the GCD is. So we're going to start with Euclid's algorithm. Okay. So we start here with 153 and 117. Okay, now we're going to find our other number, our R, by taking 153 mod 117. 153 mod 117 turns out to be 36. Okay, now we keep going. So now we're going to take 117 mod 36 and get 9. Again, we're always using those two previous numbers. Next one, we're going to use 36 and 9, 36 mod 9. And this is one we already did. So we've already done this part here. And we got down to 0, right? So what did we say? We said then we step back from 0 one step, and that's our GCD. So we know that the GCD is 9, but we don't have this yet. How do we express 9 as some integer times 153 and another integer times 117? So that's what we need to do. So now we continue on with the extended part. Okay. So 9 is the GCD, and now we're going to try to write it as a linear combination of those original numbers. Okay. So again, this was that little pattern that I wanted you to start kind of remembering. R equals y minus y div x times x. Okay, so we'll start with the GCD here, the 9, and let's say that that was our R. In the case that this, when we first found this as R, the two previous numbers were the ones we worked with, right? Okay, so we're gonna use this pattern here. So look at the two previous numbers. The largest is 117. The other one is 36. So we're going to say we're going to put 117 in place of y here, and then we're going to put 36 in place of x. So we start out with 117 minus, and then we've got this expression here. So that's going to be 117 div 36, and then times the 36. So notice again, the 117 came first as we're writing numbers, and then the 36 came last. But we had to remember that there's a minus there, and there's parentheses around here. And we have to remember that that's div and not mod. I've been known to accidentally use a mod there. But for these equations, we got to remember it's a div here. So that's one equation that we know is true based on this little thing that we just learned. But now this isn't good enough. We need to be able to write 9 as a linear combination of 153 and 17. So far, we could eventually get it down to a linear combination of 117 and 36, but we don't even have 153 involved. So we need to do a little bit more. So we're going to go back and look at the 36 too. How can we write 36? Let's remember when 36 was R. When 36 was R, we used 153 and 117. So let's use this pattern again. So we could say 36 is equal to, and then the 153 goes in for the Y, and the 117 goes in for the X. Okay, so 36 equals 153 minus 153 div 117 times 117. Now, I said it as if those parentheses aren't there. Obviously, we have to remember, we do what's inside the parentheses first, but I'm just trying to point out the largest number shows up twice first before the smallest number even shows up here. Okay, so what have we done so far? Well, we've just come up with two little equations. But let's just do something here. And this is what we're going to do every time we come up with these equations. We're going to evaluate the div function here. So inside here, it's 117 div 36. We're going to evaluate that and replace it by what the number is. So we're going to say then 117, all of this equals 117 minus, and what is this? 117 div 36 ends up equaling 3. Okay, so we're going to replace this div expression by 3. Now, here's where you have to resist the temptation. At this point, maybe 5 out of 10 people, or maybe even more, would say, okay, now I can evaluate that. I'll take 3 times 36 and then subtract all of that from 117. Well, that's not going to get us anywhere. That gets us back to 9, right? These are magic numbers here. We keep them. 117, 36. We keep them. It's just this div function that we're going to evaluate here, okay? So we keep this here, 117 and 36. And for this next one, the same thing, 153 and 117 are magic numbers. In fact, they're even more magic because they're the 2 originals, and they're the ones we really care about. So we're going to leave those there, but we're going to at least evaluate this div here. So 153 minus, and 153 div 117 is 1, equals 1. So 1 goes there, and then times 117. Okay, so what have we done? We've come up with 2 little equations that, and 36 has been written in terms of those 2 numbers that we care about. But then 9 but we need to see how 9 can be written in terms of those 2 numbers. But we've got this going for us here, so we're going to do some substitutions here, okay? That there, I just wanted to show, remember on each of these equations, we're always using those 2 previous numbers. So remember what our goal is. We need to write 9 as a linear combination of those 2 original numbers, 153 and 117. So we want to be able to say 9 equals something times 153 plus something times 117. And it's these 2 numbers that we find are going to be the ones that are so important for us to know when it comes to the cryptography part, okay? So that's why we're even trying to get to this. So we're still not quite there yet, but let's go a little further and see how we would do it. Well, starting with 9 equals this, okay, we found that 9 equals 117 minus 3 times 36. I'm going to start with that. But guess what? We know that 36 can be written like this, 153 minus 117. So, and ultimately we want everything in terms of 153s and 117s. Those were the originals, right? So I'm going to take what 36 is equal to right here and put it in right there, okay? So I'm going to, in place of 36 here, put this 153 minus 1 times 117, okay? Now we're getting somewhere. We're almost done because you see that we have 9 expressed as some different multiples of these 2 magic numbers, the 2 original numbers, 153 and 117. But 117 shows up a couple of times. And so we want to kind of clear that up, make it so that it's just one number times 153 and another number times 117. Again, don't be tempted. Well, you might be tempted, but don't follow through with just evaluating these numbers, because all you'll do is get back to 9. We want to keep the 117s intact and the 153s intact. But at this point, we're always going to have parentheses, and a lot of times we'll have a negative right here in front. So I would suggest here, you could do it in your head. I could say, well, how many 117s are there? You could say, well, there's 1 plus another positive 3 of them, so there's 4 altogether. You could say that if you're pretty good at this, but I would suggest doing it even if you are pretty good at it. Taking an extra step and use the distributive property to distribute that -3 in, because a lot of times we're going to have double negatives and things, and you can make a mistake here. So I'm going to rewrite this. The -3 can be multiplied by the 153. -3 times 153. And then a -3 times a -1. So you see what we're doing? We're distributing that -3 into both of these terms here. Okay, so -3 times 153 and -3 times a -117. -3 times -1 is a +3. Does everybody see how we got to this? Okay, I'll take that as yes. But again, slow down at this one point because it'd be really easy to make a quick little mistake here. Okay, let me read the chat here. Oh, there was something in chat. Now it's gone, I think. Okay, so if you wanted to say something, let me know. But looks like now I can't get to it. Okay, but now we're not quite done, right? We have to put those together because we've got two terms with 117s. So we've got 117 and a +3 117s. So how many 117s? We're almost treating like these two magic numbers, 117 and 163. We're kind of treating them like we would variables here, right? We're not messing with them, but we're just like combining like terms, okay? So I'm going to put the 117s together, and there's 4 of those. And then 153, there's -3 of them. So we have this right here, and we have now done what we wanted to do. Write the GCD, which was 9, as a linear combination of these two original numbers. So I could say my S, because S is what goes in front of the X, is, let's see, yeah, so the X, let me remember, the Y is bigger. The Y is bigger than, okay, sorry. What comes in front of the, so the X would be the 117, I think. You don't have to keep track of it right now, but I'm just wanting to make sure I call those numbers right. The smaller one's going to be the X, the larger one's going to be the Y. So anyway, if I'm calling 117X, then what's in front of that would represent my S. And what's in front of the Y will represent my T. Okay, questions. Can I answer any questions at this point? We are going to do another example all the way through with me writing it out on paper, and you guys can get a piece of paper and pencil right along with me if you want. But do I have any questions before we go on to the next one? Okay, if not, I'm going to get my tablet here and try to start writing. I used to use a tablet all the time, and now I haven't done it since I stopped teaching math. And so I'm not as good writing with the tablet as I used to be, but I'm going to do the best I can here. So, so let's just start at the very beginning. We want to be able to take these two numbers, 675 and 210, and write the GCD of it as a linear combination of those two numbers. And we're going to have to find the GCD first, right? So that's where we start with the Euclids algorithm, where we start with the largest number here. So 675 and then a 210. Okay, so we start with our two numbers there, and then we're going to start taking the mod here, right? So I want 6, the large number, mod the smaller number. And so when I find 675 mod 210, I'll just tell you, you would get 45. But if you were doing this yourself, you'd have to stop and figure that out. Okay, so you get 45. Now I'm going to use these previous two numbers here and say, what's 210 mod 45? That turns out to be 30. Oh, this might be another example we've already done. At least we've done the Euclid part of it. So I think maybe we already did this one where we found that the GCD was 15. But anyway, we'll do it again. Okay, the next one, we take the previous two numbers. So 45 mod 30. and we get 15. And we keep going until we get 0. So now we're going to say 30 mod 15. That's when we get a 0, right? So we're all the way down to 0. So we step back 1 and say this is our GCD. Okay, so I'm going to say, so 15 is the GCD of the two numbers. And that, if that's all we were doing, we'd be done. But the next thing we need to do is be able to write 15 as a linear combination of those two numbers. So I'll say next, we need to write 15 as a linear combination of those two original numbers, 675 and 210. Okay, so we do have more work to do. But does anybody have any questions so far on that, where we are so far? Okay. If not, now remember the next thing we would do is start writing out our little equations. Remember, for each of these R's, there was a little equation. And so let's start with the one, the first one over here to the right, except for the 0, and it's the GCF anyway. So we're always going to start with that one. 15 equals. Now, do you remember that pattern? We're going to look at the previous two, and it's going to be 45 minus, and then we have 45 div 30 times 30, right? That was that pattern. So the 45 twice here, the 30 twice here, but we have the 45 div 30 in parentheses. So does everybody remember how we would have gotten that? Okay, and let's go ahead. Remember, we want to keep 45 and 30 intact. We don't want to do anything with those, keep those there, but we will go ahead and always evaluate this div function here, okay? So the div 45 div 30 we see here is 15, right? So no, div, it's div, not mod, it's div, and that's what I forget sometimes. It's div, not mod. So div is not 45 div 30 is not 15, but it's 1, right? Because div means how many times does 30 go into 45. Okay, I've lost my ability to write. Let's see, I guess I'm back. Okay, I think I'm back. So anyway, it's going to be 45 minus, and this whole thing is just a 1 times 30. Okay, and so really that can be written as 45 minus 30. Again, keep it written like that. Okay, so we have that. We have two other R's, right, that were R's at some point. So we're going to keep going backwards and look at the 30. So for 30, we have 30 equals, and then we use the previous two numbers. So we have 210 minus 210 div 45 times 45. And now let's evaluate this. That ends up being a 4. Okay, so we're going to have 210 minus 4 times 45. And we have one more equation that we can look at, the 45. 45 equals 675 minus 675 div 210 times 210. And let's find that. That's going to be 3. So it's 675 minus 3 times 210. Okay, and those are the only R's we ended up with, right? Because the other numbers ended up were the X and Y that we started with. Now, remember, we're trying to get 15 as a linear combination of these, 675 and 210. So we need to use all of these because you see why 45 can be written as a linear combination of those two numbers. But we don't want 45 as a linear combination. We want 15 as a linear combination, right? So that's the key. That's what we want to try to rectify. We need to write 15 as not a linear combination of 45 and 30, but of 675 and 210. So the next step I would do is get back to what I'm really trying to do and want to see how I can write 15, okay? Because 15 was the GCD. Okay, well, it's 45 minus 30. That's what we have up here. Okay, but let's now, of these two numbers, we have those in these different formats. So let's start, you can do it, use any order you want, but I think probably the best way so that we can always do it right, I think let's always say that we're going to replace the lowest number here. See, 30, we know what 30 is. I'm going to change color here. 30 is this. So I'm going to write the 30 like 210 minus 4 times 45. So I'm going to say equals 45 minus, okay, now I'm going to put that in there. 210 minus 4 times 45. So all I've done is replaced, since 30 is equal to 210, then I've just replaced 30 by all of that. Does everybody see how I got that? Okay, now, again, these are special numbers except for any number in front. And let's, again, take our time and distribute through so we don't make any errors, okay? So I'm going to say we've got 45. Now let's distribute the negative in. So we're going to have minus 210 and then a negative in with a negative 4. That gives us a positive 4, right? So negative times a negative is a positive 4 times 45. So I'm just cleaning this up. Again, keeping my numbers, the 210 and the 45. I got to keep those there. I don't want to start multiplying and getting rid of those numbers. I need those. But now, remember, we really need to, we only want to write 45 once. And I have 45 and then plus 4, 45. Okay, so I'm going to put those together and say that there's 5 of them, right? 5 45s. So I'll start with the largest number first. I'll say minus 210 plus 5 times 45, right? Negative 210 plus a 5 times 45. Okay, everybody with me so far there? Now the last thing we need to do is replace 45 with what we know it to be. So let me do this. We know that 45 is equal to this, and those are our most magic numbers, 675 and 210, because those were the original numbers here. So I'm going to replace this 45 here with that. Okay. So I'll say equals negative 210 plus 5 times 675 minus 3 times 210. Okay, and now again, we'll be careful and distribute this through and all. So negative 210 plus, I want a 5 times 675, 5 times 675 minus 15 times 210, right? Right? Because 5 times a negative 3 is negative 15 times 210. And now we've got two terms with a 210, so I need to put those together. So let me start by writing the 675 part first. I've got 5 times 675, and then I have how many 210s? Negative 1 of them and negative 15 of them, so negative 16 of them, right? So negative 16 times 210. Now, we have just accomplished what we were supposed to accomplish, because we were supposed to write the GCD, which is 15, as a linear combination of these two original numbers. And we did. It's 5 times the first number, the 675, minus 16 times the other number. And so we accomplished what we wanted to for that example. And at this point, you might, be saying, well, why did I need to know how to do that? But as I said, you're going to need to know how to do that because we need to do something next time that uses it. Okay, so this time I want you to practice this, get good at it, so that you'll be able to do it easily for when we get started next time. Okay, any questions on this problem? Okay, hope you're all still with me. Now, let me just give you a preview. I had intended to talk about this today. And for you guys, I may have had time, but with my earlier class, because my internet kept going out and things, I got to this point and we'd run out of time. So, and I think maybe we're at the saturation point anyway of learning new things. So for you guys too, I'm going to stop here and not go over this slide. This is where we'll start next time. So next time we'll start here, but what we're going to be learning how to do is the multiplicative inverse, which I said we need to know for this RSA cryptography. And it turns out, so, first I explain what it is and give some examples. And again, we'll talk about that next time. But it turns out that we have to use that extended Euclidean algorithm to find the multiplicative inverse, because this line here, if it's not relatively prime, if it's relatively prime, if it's not relatively prime, then it's not going to have a multiplicative inverse. But if it is relatively prime, then see what this says. The extended Euclidean algorithm is going to find those integers s and t such that the GCD, which would be 1 in the case of being relatively prime, can be written as a linear combination of my two numbers that I started with. And then ultimately, here's what we find. That once we find s, which is that number in front of what we would consider x at that point, and we'll get to that later, but whatever s would be, we find from that extended Euclidean algorithm, then we take that mod n, and that's the multiplicative inverse. It's a long process. And I was going to do it for you here on paper again. And we'll do that next time. Gosh, we'll have to see how I'm going to be able to do this next time and the cryptography, but I'm going to see if I can. Otherwise, I'll either have to post an extra video for you to watch besides class next time, or we'll throw the timing off a bit. Now, as it stands now, I'll say this now since it's about time to go. If we look back at our schedule, and as we've said last time, right now I have the test scheduled for next Monday. So that's a week from today. So it all hinges on if I think I can talk about next time, if I think I can talk about not only, let's see, if I can talk about this multiplicative inverse, which won't be much new, anything new, because you're going to be using this Euclidean algorithm, okay? Extended Euclidean algorithm. But I need to be able to talk about this and then go on and talk about the cryptography. So that's the question. And so that's what I'll have to think about. So there's a chance, and I'll let you know Wednesday, if we might have to again push the test off on Wednesday. And I hate to have, I've done it just once before, pushed everything back, but my goodness, all of this stuff we need to cover each time, it's really hard to fit it in. And so I don't want to just say it quickly and expect you to, and half of you be confused. So I want to say it so that I can hopefully get most of you to understand. So therefore I'm getting a bit behind. So I'll try to figure out, I'll try to look ahead to see, I might be able to put this next unit in a shorter period of time. So it's possible. You guys can hope and pray that I'll find that I'll be able to move the test actually and not have it be next Monday, but maybe be Tuesday. That would give us then plenty of time to do the multiplicative inverse and then also do the cryptography. So I'll let you know for sure.
Did you just say that you were going to make a test be on Tuesday?
Did I say Tuesday? I'm sorry, I meant Wednesday.
Okay.
Right? Oh, sorry. Did I say Tuesday? Sorry. Yeah. Yeah. So we meet on Mondays and Wednesdays. So yeah, if I said Tuesday, I didn't mean that. So I'm saying that we were going to have the test on this Monday here, 2:15, and then go on to talk about induction and recursion on that Wednesday. But if I can't fit everything else in next time we meet, which is this coming Wednesday, then I might have to move that test back one. So I'll take a look at it and let you know for sure, because on Wednesday you would know anyway, because you'd know whether I was able to fit it all in or not. So I don't want to hurry us. So I'm thinking probabilities are pretty good that I might move that test to Wednesday. Okay, but I'll let you know. Move the test to, the Wednesday of the next week, but I'll let you know this Wednesday, which is next time we meet. Does that make sense? A lot of Wednesdays we're talking about and stuff. So what questions do you have? Any questions that I can go over here?
I have a question in the chat.
Oh, okay. Okay, let's see. You know what? That's weird. I'm sorry, I didn't think. Okay, sorry, thank you. I thought it looked like the chat disappeared and then I couldn't find it. So I thought somebody took away their question, but you did have it. Okay. Yes, the question was, we're finding S and T such that R is equal to SX plus TY. And does S and T have to be integers? And yes, they do. So when we talk about S and T, we are always talking about integers. Yes. Okay, good question. Anything else for now? I'll tell you what.
I have a question about
yeah, go ahead.
the test. Are we just gonna use UJA proctoring for the test during the class period, or is it set up?
Okay, so this is where you'll need to have your webcam. And what I'm going to have you do is, like, all of you that are on there now, you have your webcams turned off. So I'll say to take the test, you need to turn it on. So like I would be looking, let's pretend like I'm taking the test now and I'm a student, and you're the teacher. Then you would just be watching me this whole time take the test. I'd be writing stuff down. I'd be going up to the computer typing things in or whatever. And I'm just watching. Just, obviously I can't keep you, some things I, can't keep you from doing, but I can for sure tell if you're not getting help from somebody, right? Because I'm not, seeing you look over and talking to somebody or, that kind of thing. So it's I'm not going to use Yuja just because it's a little bit awkward. And sometimes the uploading and stuff like that, depending on people's internet can be difficult. So I'm just going to kind of in real time watch everybody. Okay.
Okay.
So that makes
Okay,
sense.
that makes sense.
Okay. And just so you know, somebody asked in my last class, if you're going to be able to use notes or whatever, I'll talk a lot more about the test on whatever day ends up being the day before the test. But, there's some things that, when there's a lot of stuff like this, let's say this, this algorithm that we just learned today. Ideally, I'd like everyone to be able to do the whole thing without looking at any notes. So I'd like, and the thing is if you can, that's when you're going to have plenty of time to do it. So I'd like you to plan on not having to use your notes for this and for basically anything. But again, I can't know that you're not holding up your notes, right underneath or something like that. So I can't, say don't, because then the dishonest ones would do it and the honest ones wouldn't. And then that's, not fair. Everybody didn't get, anyway. So I guess the bottom line is going to be that I usually try to write the questions so that if you understand it and know it, then you can answer that fairly quickly and you don't have to be looking through your notes. But if if you're saying, I just don't know it very well, but I'll have my notes close by, then that'll help me. But then when you get to a problem, then you're going to have to look through your notes. And if it's too obvious, I might say, let's, don't look through your notes. But even if that's not the case, and even if you were trying to look through the notes in a way that I couldn't tell, you wouldn't be able to look at it, find it, and be able to figure it out. So basically it comes down to hopefully knowing it so well that maybe you could do everything if I told you don't use your notes, but I'm not going to say don't use your notes. Does that make sense? Hopefully that kind of makes sense to everybody, but I'll talk more about that next time too. So, okay, good. I'm sorry, I better let you go. Any other questions? Stick on the line if you have other questions. Otherwise, I'll let you go and we'll talk next time about multiplicative inverses and hopefully get to cryptography. And I'll let you know then when I do plan to have the test. Okay, see you guys. This is, Monday. So I'll see you on Wednesday. Bye-bye.